Okay, and yeah, I'll get started here. As a reminder, if you have any questions along the way, be sure to ask them in chat. I have that open, or just speak up and ask. Either works. Um, I will be monitoring that to see if anyone needs any help. And yeah, so this week, you guys have, or this past week, you have been learning about transfer functions. So, transfer functions on a very basic level are functions that represent some input or some output over some input. In circuits, we say that usually the output voltage over the input voltage is equal to h of omega. So these would be complex where omega is the frequency. So if I have some circuit that right now you would probably see drawn as something like V in, and then you'd have some components. And then I had some output. Then the transfer function for this circuit would be whatever that output voltage is. And you can think of this as kind of just a voltage source of V in. So you can think of this H of omega. If you remember that inductor would be, I'll actually write this as J omega L, and this would be 1 over J omega C. So this transfer function would be whatever V out over V in is. And honestly, for anything that you guys are probably going to be expected to do on a quiz, it'll be something probably pretty similar to this, because anything that's much more complicated than this is just too much algebra and it would take too much time. So for this particular example, though, if you look at this, V out is just the voltage over that inductor. So here, oh, an easier way to write this, or some way that people might find it easier to think about it, is you guys are used to finding some voltage in terms of an input. So you can see if you just rearrange the algebra a little bit, you get this. So if we want to say what's V out in terms of V in, then that's pretty straightforward. That's just a voltage divider. So that would be V in times JWL over JWL plus 1 over J omega C plus R, right? Uh, and you could do a bunch of algebraic rearrangement on that if you wanted to. I'm not going to right now because this is just an example. But then what you get here is that, V out over V in equals H of omega, because that's what we call it, equals, in this case, J omega L over J omega L plus 1 over J omega C plus R. And that would be your transfer function for this specific circuit. In general, that's all a transfer function is. It's not much more complicated than that. Um, some other terminology, the magnitude of a transfer function. So if I have the magnitude of h of omega, um, I think someone might be unmuted. Make sure you check that. The magnitude would be the real part of h of omega squared plus the imaginary part of h of omega squared. Same as like any complex number. What else we got here? Again, similarly, the phase of h of omega is equal to the tangent inverse of the imaginary part, just not actually writing the omega because I'm lazy, over the real part. And last but not least, if we're dealing with a voltage signal, which you will be for the purposes of this class, then if we want to write this in decibels, decibels is like a logarithmic scale for numbers. If we have some voltage, then that voltage in decibels, which we write like this, would equal 20 times the logarithm of that voltage. This is log base 10, not natural log. So yeah. So if I then asked for, so that means that h of omega in decibels would be 20 times the log of h of omega. And hopefully you all remember your logarithm algebra rules because that'll be pretty relevant here. I'm not going to explain them here. I'm just going to do them on some example problems. And then last but not least, there's like a standard form for h of omega, and that would be all uh k j omega, or all like, yeah, I'll just say k j o all j omegas in form uh j omega over omega c. Make sure I'm writing this down right. I think I am. Yeah. Or it would be actually better way to write that, more accurate to the class, would be j omega over omega c, and all real components of terms are 1, and all other coefficients factored out. Again, I'll get to this in examples. Um, yeah, I think I don't really, I'm pretty sure you won't have to do Bode plots on the quiz, so you shouldn't have to worry about that. So without further ado, then I'll just get into some example problems. Yeah. So to start with, I'll do something very similar, almost identical to the example I just made up earlier. Oh, one other thing. Um, this is if I have some circuit that has some V in and some stuff dot 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 dot. Um, the and it has some equivalent input impedance, so that would just be the sum of all of these together. Then the resonant frequency is the frequency such that the imaginary component of that input impedance is equal to 0. And I'll explain what that means in a second. That's something you might be expected to do on a quiz. Hopefully you guys know what this means from class, but if not, then I will show you an example anyway. So first example, we got some source voltage, some capacitor, an inductor, and a resistor, and we got our voltage of the resistor. And we got CLR, and this question says find transfer function, find resonant frequency, resonant frequency omega naught, and C value. I'll write in some symbols here. Value of H omega at DC conditions. So so just kind of getting started here. H of omega in this scenario, this would be our output, this would be our input, just because this is the source. So this is equal to VR over VS. And that would be, again, just a voltage divider. So we get, if I were to do the voltage divider and then divide by VS, then you'd just get the ratio of fractions, right? So here it would be R over R plus J omega L plus negative J over omega C. And then if we want to make that look a bit nicer, we would say, okay, I can factor out the J in the bottom to get it in just kind of a normal A plus BI form. So this could be J omega L minus 1 over omega C. And this is your transfer function. So it's probably going to be that simple. Like just do a voltage division. Maybe you'll have to take two things in parallel or something like that first, but nothing you haven't seen before. It's just algebra. So that would be your answer for part A for this question. So I'll box this in. B, you know, as I said previously, the resonant frequency is when the total impedance has a imaginary part of zero. So here, probably should have called it like Z equivalent because I think you're more used to that. Z equivalent equals R plus, and then we actually already found it here, right? So I'll just write it in that already simplified form. So R plus J omega L minus 1 over omega C. So then if I want the imaginary part of Z equivalent, then that would be simply omega L minus 1 over omega C equals 0. And now if I just solve this for 0, let's see, I add the that one term over to the other side, you multiply, you get omega squared LC equals 1, then omega equals the square root of 1 over LC, which is something you've seen before in this class. It's like I think they just, oh, this should be like, yeah, then you say your final thing is omega naught. And this is like a thing you've seen before in the class. This is where it comes from. I think you used it in the RLC circuit section. This is just what that resonant frequency actually is and how you get it. It's the point at which kind of you can think of it as the inductors and capacitors canceling each other out somewhat. So that would be your resonant frequency. And then for part C, all right, so for part C, DC conditions is when omega equals 0 because there's no frequency. Shouldn't that be in standard form? Can I show an example that we should actually see? Uh, Let me finish this one, and then I think one of the other examples might be in parallel, and if not, I can just make one up. Um, for this, okay, Joshua, for this specific question, it didn't ask for standard form, but if you wanted to put this into standard form, then yeah, you would have to do that. So this would become this doesn't really go into standard form quite nicely because we don't have actual numbers. This would go to like you divide by R on the top and bottom. So it would be like 1 over 1 plus J, and then you'd factor out that omega. This is like not nice to look at. 1 over J, omega over R times uh yeah, like you could write it like this. I think I think that's an equivalent algebraic expression. So then your omega C would be R over L minus 1 over C. Oh wait, no, you can't say that. That's not a thing you can do. Um, you'd have to do a bunch of you'd have to like multiply by omega C to get it in the top. Let's see. If I were here and then I multiplied by omega C, what we'd have R omega C over R omega C. You wouldn't be given something like that. Like I don't think I did this kind of seems too messy. I mean, I know I'm gonna do a question later that's kind of like that. Um, so but that's not an issue right now. Let me see this. Uh, Yeah. So yeah, they'd only ask that if the question like lent itself to do it easily. So ignore that for now. So then for this question, again, it says, okay, what about at DC? We just plug in h of 0. So that would become r over r plus j, and then, oh no, we're gonna have something scary here. 0 minus like infinity. That doesn't work. So what do we say instead? We would instead look at the circuit. So if we were at DC, right, we know what circuits look like at DC. If we look here, right, at DC, we know the inductor becomes a short circuit and the capacitor becomes an open circuit. So what that means is that we have an open circuit right here, which means no current is flowing. If there's no current flowing, then there's no potential difference across this resistor. So that means that this would become 0 because the voltage of the resistor at DC equals 0. And that's what you would say for that. Okay. What can I do next? Yeah, I'll do this one next. So we got, yeah, we got h of omega equals j omega LR over 2r squared plus j 3 omega LR. And we want to find the corner frequency find the corner frequency, um, find simplified expression for the transfer function, the magnitude of the transfer function in decibels, and estimate the value of the transfer function for omega is much greater than the corner frequency. So first, we want to find that corner frequency. So how would we get started with that? So to find the corner frequency, if you remember from class, or as I said earlier, standard form has all the terms in terms of like omega over omega c, where omega c is the corner frequency. More specifically, omega c is the omega like such that h of omega c equals, I think it's like 1 over root 2 of h of omega 0 or h of 0 or something like that. But it's when the transfer function is at 1 over root 2 of its maximum value. And that's because that's the point where the power is halved, and that's what has been decided is when the cutoff is for that function. Um, but here we just want to put this into standard form. So standard form for this, well, how are we going to turn this into standard form? So we want to make this term and this term going to be in the form of just omega over something. So if I want to do that, I would, oh, and the other thing you want to do, actually the main thing you want to do, my bad, is you would want to make this 2r term a 1. So what you do is multiply this by 1 over 2r squared over 1 over 2r squared. And then you would get j omega LR over 2r squared over 1 plus j omega j 3 omega LR over 2r squared. This would cancel with that. This would cancel with that. And then that would become j times omega L over 2r over 1 plus j times 3, or I'll say omega 3L over 2R, which you could rewrite as J omega over 2R over L over 1 plus J um, omega over 2R over 3L, right? So then what we'd say is the corner frequency for this then would be, I think, just the lowest one. And in this case, 3L is going to be a bigger number than L, or 3L is going to be a bigger number than L. So then if this is like corner frequency 1 and this is corner frequency 2, in this case, corner frequency 2 would be less than corner frequency 1. So then, oh no, actually what it is it, this question's kind of vague. Let me remind myself of the formal definition of this from his notes or how he would do this. Um, mm, okay, well, for this question, actually, what I think it is since this one's in the denominator, right? While I said that you don't really need to know about Bodhi plots for this exam or for this quiz, probably, if you think about how this plot would look, the one on the bottom would cause the magnitude to go down because it's in the denominator, right? So one of them would be kind of pulling the function down, and the other one would be pulling the function up. So what we actually care about in terms of this like cutoff frequency is when the magnitude starts to go down. Because if we were using this as like a filter to only let only let low frequencies pass and cut off the high frequencies, then you would want the cutoff to be when it starts going down. And in this case, it starts going down at that point. So we would say that omega c of the cutoff is 2R over 3L. Yeah. So then the next part of the question says, find the simplified expression for the magnitude of h of omega. So to do that, we have to remember our log rules. But first off, right, the h of omega equals the real part of h squared plus the imaginary part of h squared. So what this then is going to be is ugh, is going to be um it says, yeah, let me remind myself how this works. You see that? Oh yeah, okay. Basically, if we have if we have h of omega, we can rewrite this now as like j times omega over 3 omega corner frequency 1 plus j omega over corner frequency. So the magnitude of this kind of expression is going to be equal to the magnitude of the numerator over the magnitude of the denominator, right? And then if we want to find this in log form, then it would be, I wrote this in a bad order. So we have this, right? And then the log of magnitude of h omega then would be equal to the log of the magnitude of the numerator minus the log of the magnitude of the denominator, just by like logarithm rules. So in this case, right, the magnitude of the numerator is just going to be, judging by this expression here, it's just the imaginary part. It's just the imaginary part because there's no real part, right? And since we're actually looking for this in decibels, it's going to be 20 log. So this is just the log rules, but then Yeah, so if we're finding h of omega in decibels, decibels is not just log, that's equal to 20 log the magnitude of h omega, which would then be 20 log omega over 3 omega c minus, because we have that denominator there, 20 log, and then here, since you actually have a real and imaginary part separate, it would be real, or it would be the square root of that 1 squared plus omega over omega c squared. And then you can separate that out, or you can do a few more log rules to this. So this would become 20 log omega over 3 omega c minus 10, because this is like to the power of 0.5. You can factor out that and multiply the numerator or the coefficient by it, sorry. So 10 log 1 plus omega over omega c squared. And then if you want to simplify it even a bit further, you can actually separate out this first term a little bit. So this would become 20 log 1/3. This just kind of gets it into the most straightforward form you can get. Okay, I'm gonna take a sip of water. So this would be your simplified log form.
Did you subtract the 20 log the third minus 20 log W over WC since it's like a fraction?
Uh, you wouldn't subtract the 1/3, but what you could do instead is subtract log 3. Does that make sense?
Yeah, yeah.
Yeah. But yeah, same thing. It's just sometimes nicer to leave things in like positive form. Yeah, you're right though. You'd get full points either way. So this would be your answer for the second part. We found that simplified expression. And then estimate the value of the transfer function for omega is greater than omega c. So if omega is much greater than omega c, then a couple things happen. Let's just say it's like 1,000 or something, and omega c is like 10, right? Then so if omega is greater than omega c, then what we can say is, since the log function is strictly increasing, right? Or I guess this is probably a better way to say this. Mm, uh, the main part here that I think you actually deal with is this section in the last logarithm, right? Because if you have omega over omega c there, and then you have 1, that omega over omega c term is going to get much bigger than the 1. So you could say that this then sort of equals, or is approximately equal to 20 log of 1/3 plus 20 log of omega over omega c. And then this 1 would disappear, so then you'd have a 2 here, and the 2 would go to the front. So this would be minus 20 log of, this should, yeah, 20 log of omega over omega c, right? And then what you see here is actually, okay, this and this cancel, and then we are left with just 20 log of 1/3, which turns out to be roughly equal to negative 9.54 decibels. And this might look kind of weird. You'd be like, okay, how did we get a constant number, but we had a function? The key thing here is that if you think about it, I'll kind of go into the Bodhi plot real quick. This isn't important for like getting your question right or getting the answer right to this question. But if we have this in standard form, right, this term on the top in a log plot is going to just be an increasing line. But then this term here, right? Oh, and this was actually, oh no, it's just that. Okay, we have an increasing line here, and then once we get to our second, hold up, actually, I need to re-pull up this graph from the textbook that has all of this. If you're asked about Bodie plots, you'll be given this graph. Um, so, oh yeah, that's what it is. Okay, so I actually wrote this in standard form incorrectly. My bad. That the proper standard form for this would be it would be L over 2R J omega over 1 plus J omega over 2R over 3L. The J omega terms always stand on their own, and like I actually said earlier, you always factor out that constant. So what this here would be is it would be like starting at whatever 20 log uh L over 2R is, and then it would be going up at a slope of 20 decibels per decade, which is like 20 decibels every factor of 10. And then when we get to whatever 2R over 3L is, you can think of it as like here we have another graph that's like this going down at negative 20 decibels per decade. And that's represented by this term. And then when you'd like add these together, you'd end up getting a graph that looks like that. And this here would be your value for omega c is, or for omega is much greater than omega c, and that would be your minus 9.54. I like messed something up because this should be a negative. I like looked at this graph wrong. This is probably actually like down there. Um, yeah, but that, but basically you'll have like one going up and one going down, and they'll cancel out as you go to infinity. So it does make sense. It's always good to, once you get an answer, think about it and say, does that make sense? Because if it doesn't make sense, then you probably got it wrong. So yeah. And then, okay, last question I have is very similar to the first one I did, but now we actually have numbers. So you'll actually get a numerical answer. Actually, is this one? Yeah, this is worth doing. It's ever so slightly different, but very similar. So we have our Vn, a resistor, an inductor, a capacitor, and then you got your V out. This is 20 ohms, this is 0.1 henries, and this is 10 microfarads. If we, and the things it's asking us to find are find the resonant frequency omega naught and find magnitude. I don't want to write out that whole sentence. I'm just going to write it symbolically. The magnitude of the transfer function at said frequency. So here, if we want to find our resonant frequency, again, that is going to be the point where the imaginary part of the equivalent resistance of our whole circuit or equivalent impedance equals 0. The equivalent impedance of our whole circuit is going to be R plus negative J over omega C plus J omega L equals plus J omega L. If you write this to in a nicer form to find the imaginary part, you would get J omega L minus 1 over omega C. This is the exact same thing we found in that other question. I'll say a dot, dot, dot. You'll end up getting that omega naught equals 1 over square root of LC. If you're curious, remember we did this right here. This is just a similar quiz question, but this time we have numbers. So then if we actually want to find out what this is, we would then say, okay, I have L and I have C. We got 0.1 times 10 times 10 to the negative sixth. If you plug both of those in, then you get 1,000 radians per second is your resonant frequency. And then if we want to then say, okay, what is the magnitude of the function at that resonant frequency? Well then, okay, first we have to find the function, of course. So the function is just going to be, as it was before, it's going to be that impedance of our capacitor in this case over the total impedance. So that would be negative J over omega C over R plus J omega L minus 1 over omega C. And then if we want to find the magnitude of that, then that would become the magnitude of the numerator divided by the magnitude of the denominator. So that would become 1 over omega C, simply, over the square root of R squared plus omega L minus 1 over omega C squared. And then if I simplify this a little bit by multiplying the top and bottom by omega C, this is just you could really just like plug this stuff in earlier. Like you could plug this stuff in right now and you'd get it, but I'll simplify it a bit more just because it can look nicer. Remember, if you multiply something that isn't squared into a square root, then you'd square it. So this would become in the square root, we'd have r squared omega squared c squared plus uh, omega squared L C, because this is already in a square. This is just like algebra. Again, this part really isn't that necessary. And then omega c times omega c would be in there. And then if we then were to plug in, so this is kind of doing it all symbolically, and then we can plug it in at the end. So if we were to plug in that omega equals omega naught equals 1 over LC, you know, we would get yeah, we'd get where are we? Yeah, you get the square root of, I'll leave this omega squared as an omega squared for now. But as you can see, if we plug in LC or square root 1 over square root of LC for this omega squared, then it'll become LC over LC minus 1 squared. So that's 0 squared, that goes away. And then this is 1 over the square root of all that. So then that's just 1 over R omega C. And we know what that is. Wait, let me make sure I'm doing this right. Yeah. So that would be equal to, like, you can just plug in numbers really whenever here. So this would be, this is kind of an uglier way. L C C, bad handwriting. Anyway, you'd plug in numbers. So here L is R is 20. This is 1 over uh we did this earlier, so this is actually we already know what omega C is. So yeah, 20 times 1000 times 10 times 10 to the negative 6, which gets you 5 as your final answer. So that was kind of way too much algebra. With the parallel component example, I don't actually think that that'll be on the quiz. Like he did that in class, and I think that's why it was in my head. But judging from past quizzes and also talking with Zorman, I really don't think that'll be on there. I can do a quick example though. We still have like 15 minutes. But yeah, with this kind of question, like you can do as much algebra as you want. I kind of did too much there. But the general gist is you find your omega naught, and then you could just plug it in from here and you'd get the same answer. If you are comfortable typing in that much stuff to your calculator. Like starting from here, if you plugged in your R, omega, and L, you would end up with 5 as well, because it's algebraically the same expression. So let's see, can I make up a quick transfer function here? Let's say we got a resistor, and then instead we have a um wait, there was a question I saw. Where was this one? I wanted to do. Where is it? Give me a sec. Maybe that was in his notes. That might have been in his notes. I think that was in his notes. But I'll do this. So if we have like this, right? I suppose this could be something you'd get as well. So if we have our V in and our V out, and we have L and we have C and we have R, and we want to find a transfer function for this, again, it's pretty much the same thing we've done before. It's just that instead of having one resistor here, we have two, so you treat them as in parallel. So you can think of this circuit as your resistor and then some impedance box, and that's your V out, where this Z equivalent is going to be equal to J omega L times negative J over omega C over J omega L minus J over omega C, which you can simplify. The omegas cancel. This becomes a positive one. So that would become LC over uh, J um, omega L minus 1 over omega C, which you can write as negative. You can write that as a, what's the nicest way to write this? I think the nicest way to write this would be J LC 1 over omega C minus omega L. I think that's the same thing. Yeah. 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 Okay. So you have that as your equivalent resistance. So then if we wanted to say our transfer function is equal to V out over V in, then it would simply be like a voltage divider here. So this would be our R over our R plus Z equivalent. So that would be R over R plus J LC over 1 omega C minus omega L. And that would be your transfer function. And if you wanted to put this in standard form, you would have to multiply, I think it would be a lot of work. And I really don't think he'd ask you to. Because let's see, you multiply the top and bottom by that denominator there. So it's a whole mess. Yeah, he will not give you a question that requires a lot of algebra because like he cannot you can't expect people to do that much algebra in like a 20-minute quest in a 20-minute question, 20-minute quiz. Also, it's snowing outside. That's very nice. Go outside if you can after this. Yeah. So does anyone else have any questions? Hopefully that was useful. Again, I think the main thing to take away from this is that the resonant frequency is when the imaginary component of the equivalent impedance equals 0. The magnitude of a transfer function is the imaginary part uh, squared plus the real part squared. The transfer function is nothing but the output over the input. Which is the same as saying that the output is the transfer function times the input. And yeah, good luck on your quiz tomorrow. I think that's it for the day. I will
Uh,
end
I have a question.
Oh, you have a question? Okay. What's your question?
Is magnitude of the H omega always ZC divided by Q?
Is it always what? Say that one more time, sorry.
ZC over ZEQ?
Um, mm, what do you mean by that?
I think on question two, there's
Oh, sorry.
uh uh next page.
This page.
Yeah.
So here, the magnitude of the transfer function. Oh, in this case, it was ZC over Z equivalent. This was just the transfer function itself. And then this, I just kind of did some bad math notation. Uh, so this is here it was ZC over Z equivalent because this is the voltage divider. You have, remember, V out in this case would be V in times ZC over Z equivalent, right? Because if you have a voltage divider, it's the thing you're looking at divided by the total resistance. And then here, if you rearrange this, you'd get that V out over V in equals ZC over Z equivalent. And then if I wanted to get the magnitude of the transfer function, it would be the magnitude of Z capacitor over Z equivalent. And that's
Okay.
what I did here.
Okay.
I just kind of did that math not very clearly. Yeah. Okay. Hopefully, hopefully that's all. I will actually stop the recording now.